Assalamualaikum and very good day. So welcome back to the chapter 6, but now we proceed with part 2. Okay, for friction and minor losses topic. Okay. Okay, so for part 2, at the end of this video, we expect that you'll be able to determine the energy loss for flow, which is flow through a sudden or gradual enlargement or contraction of the flow, and the entrance or exit loss when the fluid enters or leaves a pipe from a static reservoir. Okay, so this is the topic outline which is I include in the video for part 2. Okay, so first of all we will learn what is the resistance coefficient which is involved, okay, in this part, and then we will learn about the minor losses in a certain condition. Basically, there are six main condition, which is at entrance loss, exit loss, sudden enlargement, gradual enlargement, sudden contraction, and gradual contraction. Okay, so this six part is very important part that you need to focus more later on. Okay. Okay, so first of all, okay, we need to investigate or recognize first potential source of minor losses in a pipe in a fluid flow system. Okay, so let's see the next slide. Okay, whether you can identify or not some sort of the losses occur in a pipe fluid flow system. Okay, so based on the diagram here, okay, we try to understand, we try to investigate, okay, in which that where is the potential of energy loss, okay, in a system here. So basically we want to move the liquid from this reservoir here into the second tank here. Okay, so as the liquid flows here, okay, there could be loss here because it leaves the tank, okay, from huge space into a smaller space because the diameter of the pipe here will be reduce the space of the pipe flow of the liquid flow. Okay, and then here, okay, the liquid start to enter the other section, which is become bigger here. Okay, so here, which is we call it as a sudden enlargement. Okay, and then here, from bigger to smaller, also another loss, and we also have bend here, okay, like kind of elbow shape. So here could be a potential of loss as well. So we have two bands here, one and the second one here, okay, and then we also have valves here. Okay, so there is a loss as well when the liquid flow through valves here. Okay, and in fact the types of the valve also give an effect towards the loss occur in a system. Okay, and then after that the liquid enters from a smaller space to a bigger space, also loss here. Okay, so let's check it out one by one. The example of losses occur in a fluid flow system. So, what is resistance coefficient? Okay, so energy loss is actually proportional to the velocity head of the fluid flow system, which is flow through whether it is elbow, enlargement or contraction section or valve. Okay, so elbow, I think in the previous slide I already show you how the shapes of elbow. Okay, so where there could be potential losses at this elbow. So enlargement or contraction. So what is the difference between enlargement and contraction? Okay, so enlargement, okay, for example, it is from a smaller, okay, so it goes to the bigger section. So this one is kind of, we call it is an enlargement. What is contraction? So it is opposite. So for example, from the bigger to smaller. So this is compression, this is enlargement. Okay, and WAF is just a WAF. Okay, so there are many types of WAF, so we will talk about it later. So this is the main equation to calculate the energy losses in a system, okay, in which that K basically the is referred as the resistance coefficient, and this K is actually strongly affected by geometry of the device and velocity of the flow. Okay, so I repeat again, this is the two parameter which is affect the most on K, which is geometry of the device and velocity of the flow. Okay, so later on we will discuss how can the different part which is involved in the fluid flow system and how can this different part may affected by the geometry and velocity of the system. Okay, in order to determine the value of K, then we have the K, then after that we will able to calculate the HL. Okay, so from the image here, you can see that this is a common part which is usually used in a piping system. Okay, so for example, here we call it as a coupling. Okay, and this one is a hex plug, 45-degree elbow. Okay, bushing, cap, cross. Okay, bell reducer, 90-degree. An elbow, nipple, T, 90-degree elbow, okay, and union, okay. Okay, let's start with the first part, which is we call it as a sudden enlargement. So the sudden enlargement is look like this, okay, in which that the flow will go from the smaller diameter pipe into a bigger diameter pipe. Okay, so for example, the smaller one we label as D1 and the bigger one we label it as a D2. Okay, so what happened is when the liquid flow through this system, okay, the velocity will abruptly decrease. Okay, so the V here will decrease from 0.1 to 0.2. Why? Because there's a turbulence here, okay, which is occur at this point, and this will generates the energy loss, and this energy loss is actually um, depends on the ratio between these two part here, between the D1 and D2. Okay, and yet we're still using this equation to determine the energy loss, okay, which is that V1 here is actually stand for velocity of the fluid at 0.1. Okay, and how about K? Okay, so for K I will explain later. Okay. Okay, so for example, the K is actually can be predicted from this equation if the V1 is actually 1.2. Okay, so imagine that the flow from a smaller pipe to a bigger pipe. So V1 here, if it's 1.2, so you can use this formula directly in order to determine the K value. But if it's other than that, for example, V1 is equals to 3.0, for example. So you cannot use this formula. You have to use the table. So what table that we can use? This is the table that we can use. Okay, so for example, on the left side here, we have the ratio between D2 divided by D1, which is that the D2 is the diameter on the larger pipe and D1 is actually diameter on the smaller pipe. So you have to get the ratio and you have to check what is your velocity. Okay, so for example, okay, if D2 divided by D1 ratio is 2, so for example your D2 divided by D1 is 2, and then your V is 0.6, so what is your K? Okay, so just like this. Okay, so this is your K value. Okay, so what if V is equals to 3? What is your K? Okay, so for example, if V equals to 3, like this, so your K value is 0.52. Okay, I hope that you can understand how to use this table to calculate the K value. So once you have the K value, you know that the formula is HL K V1 to the power of 2 divided by 2G. So once we already have the K value and we are given the V1 value, and of course G we know the value 9.81, so definitely we will be able to calculate the HL value. Okay. Okay, so in the case that if your value or the value given from the question is not available in the table, okay, so you can use this chart. Same concept in which that you still need what is the ratio between D2 divided by D1, and you need to know what is your V1. Okay, so V1 here is actually, there are many lines here, okay, which is represent the different value of V. Okay, so for example, the outer one here is 12 and the upper one here is a line for 0.6. Okay, let's try with example. So for example, if that the D2 divided by D1 is equals to 3, is just this one. Okay, and the V equals to 12. Sorry, it's not 1.2, it's actually 12. 12. Okay, so what is your K? So just get the intersection there and you will get your K is equals to 0.64. Very easy. Okay, I repeat, you just need to know the D2 divide by D1 on the x-axis. Then you go straight and let it touch on the V1 line. Okay, so once you get the cross section, just go to the y-axis to get the K value. Okay. Okay, let's try with this example for sudden enlargement. Okay. So the question said that determine the energy loss in water which is flow at 100 liter per minute. So this one is actually the flow rate through a sudden enlargement. So this is the shape of sudden enlargement made from copper hydraulic tubing. Okay, the small tube dimension is 25 millimeter for outer dimension. So this one is actually D outside. So I can label as DO1. Okay, with the thickness of 1.5 millimeter wall, and the larger tube here, okay, is actually 80 millimeter times 2.8 millimeter wall. Okay, so this one is actually DO2. Okay, O refers to the outside diameter. K2 is referred to the location which is at point 2. Okay, so refer appendix G2 for tube dimension and the area. So even though from the question here, it just give the outside diameter, okay, but you can use the information given here, okay, in order to determine the D1, the inside diameter, and also the area, okay. So let's see how can we solve this problem. Okay, so as usual, the first thing that you should do is just list down all the info and plan your formula. Okay, So basically, this is the formula that you can use. Okay, we know that we have to use this formula. HL V1 to the power of 2 divided by 2G. And V1, we can get it by dividing between flow rate Q divided by A. Remember that the Q is given 100 liter per minute. Okay. And then K, you need to get it from the diagram. Okay, the graph that I show you just now. Okay, so let's see what is the information we have from the equation. Okay, so the equation tell us that the outside diameter for DO1 is 0.025 meter and the thickness is 0.0015 and the area is not given, but we can get it from appendix G2. Okay, because the equation already provide us the pipe is actually made from a copper tube pipe. Okay, and the larger diameter, the larger tube is actually labeled as DO2. Okay, so it is 0.08 and the wall thickness is 0.0028. And same, the area is not given, the area of that larger part, so we can get it from the appendix, it's not a problem. And the gravity acceleration, we know that is 9.81. Velocity is not given as well, but we can get it by using this formula. Okay. And flow rate is given, but it is in the unit of liter per minute. So you have to convert it into unit SI, which is meter per second, so that it will easy for you to use it with other parameters. Okay, so let's check it out. How to solve it. Are we able to substitute it into the equation? Okay, so we already have the information and we not able to solve the equation yet until we get all the info which is we need to get from appendix, and also we need to substitute into here to get this value. Okay, well, this is table G2 in which that we will use this table because we need the information about the inside diameter. Okay, the information given to us is outside diameter and wall thickness, so we need to get what is the inside diameter and flow area. Okay, so the table, we're using the correct table, which is this one is for steel and copper hydraulic tubing. Okay, so let's start with the smaller diameter D1 first. So it is given that our diameter is 1.5 and thickness is, sorry, our diameter is 25 and the thickness is 1.5. So this is our inside diameter, 22 millimeter, and the area is given here, 3.801 times 10 to the power of minus 4. And this one is for bigger diameter, which is, this is the info given to us. Okay, so directly from the table here, we get the D2 and A2 as well. Okay, so easy. From the table, you can get these 4 information which is needed to solve the question. Okay. Okay, so based on calculation, okay, I already got my D2 divided by D1. Remember that this value, I got it from the appendix, table appendix G2. Okay, and V actually I can calculate it by using V equals to Q over A. Okay, Q is given, which is 100 liter per minute, but this one should change first into unit meter cube per second so that I'll be able to use it. Okay, then after I got these 2 information, I can use the table. Okay, so we have 3.882 for the ratio D2 divided by D1. And we go straight to the velocity here. Okay, this one is quite tricky because you need to see that the flow is, the V is 4.385. So it is between the line the line for 3 meter per second and the line of 6 meter per second. Okay, so along here is actually very tricky Okay, this one which is 3 and 6. So the 4 is somewhere over there. Okay. And finally, you will get what is your K, which is the intersect between D2 divided by D1 and the V1, which is 0.74. Okay, so here I will show you again how do I substitute into the formula. Okay, so I show you again, this is the formula that we have to use. Okay, so first of all, you need to get what is the V1 from this equation. Then after that, you need to get what is the K from figure 10.3. This one I already showed to you, which is that K equals to 0.74. In order to use this figure, you need to get what is the D2 divided by D1 ratio and what is your V1. So based on these two value, you use this figure, you'll be able to get the K value. Okay. So here is the answer. Okay. So this is the value that I get from the appendix for D1, which is 0.0222, and D2, okay, A1 and A2 from appendix directly, and this one is flow rate. Okay, remember that the question given us, the flow rate is actually 100 liter per minute. So I convert it into this SI unit. So the flow rate is actually 1.667 times 10 to the power of minus 3 meter cube per second. Okay, so once I got my Q, I can directly calculate my velocity, which is Q divided by A1. Okay, so this is my new V, which is 4.3, sorry, it's actually 4.385. Okay, and this one is the ratio. So I just get this value and substitute into this one. D2 divided by D1. Okay, and then I got my K value from the figure. Then after that, I will substitute this one into this equation. Okay, V into this value. Okay, then I will finally get my HL. Oh, this one is just, I just show you again how do I get the K value. Okay, and lastly, I've managed to get my HL, which is 0.725 meter. That's it. Okay, next we proceed with another part, which is acid loss. So what is acid loss? Okay, so where acid loss usually occur when the fluid flows from pipe into a large reservoir or tank. So what happened is at this time, okay, so this is the diagram for acid loss, okay. What happened is the velocity is decreased to nearly zero. So for example that it is from a smaller diameter and it goes to the tank here. So the velocity at this point we lost, which is nearly to zero, okay. So in this case it's very simple. The K here is actually equals to 1. So regardless what is the form of the axis here, the K we keep it as 1. So we can just calculate the HL value directly from this formula. Okay, and V here is actually referred to the V1 here. Okay. Okay, so let's try this example in which that involve the exit loss. Okay, so based on example here, stated that the energy loss in water flow at flow rate 100 liter per minute from copper hydraulic tubing at 25 millimeter outside diameter, and this is the thickness into a large tank. Okay, so if you can see here, this is the same Q that we use in the example 1, and this is actually the same outside diameter that we use in example 1 as well. Okay, so it says that it is flow into a large tank. Okay. Okay, So let's see how can we solve this problem. As usual, you need to list down all the information that we can get from the question, and you need to plan the solution. Okay, so basically this is the information that we have. Okay, so the question asks us to determine what is the energy loss. So we want to know what is the HL. Okay, from due to the exit loss. So we know that the exit loss, for example, is actually like is escape from a smaller into a larger diameter, okay, a larger space area. Okay, so we do have information for the small tube size, which is 0.025, and the wall thickness is also given. And it is the same like example 1, in which that we can get the area from the appendix, okay, table G2, okay, appendix G2, and acceleration G, we know about this information, and V1 is not given, but we can get what is our V1 based on the formula V equals to Q divided by A. And of course, the flow rate is given in this case, which is 100 liter per minute. Okay, so this Q, when you change the unit, so you can substitute into this equation, and we can get the V here. Okay, so here is the formula to calculate the HL. Okay, remember that for exit loss, the K is equals to 1. Okay, and this is the V1 that I told you just now. We can directly calculate by using Q divided by A1. And the A1 here, we can get it from the appendix. Okay. Once we already have the information and we find the value that which is need to get from the appendix, okay, for example, we need the A1, okay, and D1, okay, so we can just substitute into the equation here. Okay, so based on the D here, we also can get the A1 from the appendix, so we substitute into here. Okay, and finally we can also use this Q, which is already converted into SI unit, okay, and divide by A, so I will get the V1 here. Okay, and once you get the V1, you can substitute directly into this HL equation here, and lastly you will get your HL equals to 0.98 meter. That's it, very simple. Okay, next part is gradual enlargement. Okay, this is how the gradual enlargement looks like. Okay, in which that we'll see that this is the smaller part, and before it goes to the bigger radius part, okay, it has kind of like cone shape, which is it has its own angle. Okay, and then the flows will enter to the bigger radius section. Okay, so as you can see that it will reduce the effect of the balloon compared to the sudden enlargement. Okay, so for this one we will use this equation, the same equation, but K we need to get by using a certain method. Okay, so what happened is the energy losses in the gradual enlargement is much more smaller compared to energy loss in a sudden enlargement. Why? Because in a gradual enlargement, okay, so for example, this is the smaller pipe and we want to move the liquid is actually from smaller to a bigger pipe here, T2. So what happened is we installed kind of a conical, it has kind of a conical shape here. So this cone, of course, it has certain angle. So by installing or adding this cone shape here, it can reduce the energy loss, okay, compared to if we directly uh, move the liquid from a smaller pipe into a bigger pipe. So this is actually the diagram for sudden enlargement. Okay, so as you can see, it didn't have any cone shape here, which can slow down a bit the flow. Okay, so this one may cause a higher or more energy losses compared to this one. And the velocity V1 here is actually velocity at this pipe, okay, the smaller pipe. And K is actually depends on D2 divided by D1, which is the ratio between the bigger pipe divided by the smaller pipe, and the cone, the angle of the cone here. Okay, so in order to determine the K, it is relies on the ratio between D2 divided by D1 and the cone, the angle of the cone. Okay, and the minimum energy loss can be obtained is at theta equals to 7 degree. Okay, so the way to get the K value is the same, that you can use the diagram. I'll show you later how to use this diagram, but the concept is still the same with the other part or the other condition, in which that you need to know what is the ratio between D2 and D1, and of course you need to know what is the angle at the cone here. Okay, so once you get the intersection here, and you can get the K value directly. Okay, so this is the graph that we can use, okay, to determine the K, which is occur in the gradual enlargement. Okay, so for example, we need to know what is the ratio between D2 divided by D1, and also the cone angle here. For example, we have the 60 degree until up to 2 degree. And so with these two value, you can get what is your K here. Okay. So the diagram that I show you in a previous slide is actually experimental data. Okay. So the data also available in the table like this. Okay. But the easiest way is use the graph. Okay, because there are conditions in which that you may not have the value by using the table here, so at least you can estimate it directly based on the graph. Okay, so let's try to do this example for gradual enlargement. Okay, so let's take a look at the question here. Okay, the question asks you to determine the energy losses in water which is flow at 100 liter per minute from a small copper hydraulic tube through a gradual enlargement having an angle at 30 degree. Okay, and the small tube has a diameter 25 millimeter for outside diameter. This one is actually D1, and for the outside diameter for the larger part is 80 millimeter. Okay, so if you can see here, okay, from example 1 until this example, I keep using the same specification so that it will be easy for you just to understand the concept. Okay, and just want you to get familiar how to use this table. Okay, so how can we solve the problem? Okay. Okay, so this is the solution for example 3, which is involve gradual enlargement. So first thing first that you should do is just list down all the info provided from the question, and you need to sketch your formula plan to solve the problems. Okay, so from the solution, from the problem, from the question, it asks you to determine the energy loss, which is involve water that flows through a gradual enlargement. Okay, so it's clearly asks us to get what is the HL. Okay, so the question do provide us information, which is the angle of the gradual enlargement. The cone part is the angle is 30 degree, and this is the dimension, which is the smaller tube is 0.025, and the wall thickness is given, and the area is not given, but we can get it from appendix, and the larger part dimension also given, which is 0.08 with the thickness given. Same case as A1 for A2 as well. We can get it from appendix. Okay. And the G, we know that it is 9.81, even though it is not provided from the question, but this is actually the general information that we should know. Okay. And the V1 is not given as well. And flow rate is 100 liter per minute. Same as the previous example before, we do need to refer to tables appendix G2. And then flow rate, we have to convert it into SI units. Okay. So this is the formula to get the HL. Okay, the same formula. And you need to get the K. So at this time, as it is involved with the gradual enlargement, so the figure 10.6 is the figure that we have to refer to get the K value. Remember that this K value is depends on the ratio between the two sides of pipe. Okay, and then it depends on the angle of the cone. Okay. And for V1, we're using the same formula, which is Q divided by A1, okay, which is the... Right, so this is actually the figure of 10.6, okay. So we know that from this figure, we will get the K, which is the resistance coefficient, in order to calculate the HL, okay. So you need to do a little bit calculation, in which that you just need to find the ratio between D2 divided by D1, which is in this case we got the 3.882, which is this one will be our x-axis value. Okay, this one is roughly the location of 3.882. Okay, located here. And then the theta is 30 degrees. So theta 30 degree is somewhere here. So as you can see, the line for it is actually along here. So we just assume that it just goes extend to here. Okay. So this is the cross section. And finally, we will get the answer is 0, K equals to 0.48. Okay, so you need to use this table to get the K value. Okay, in order to get the K value, the value on the x-axis, which is a ratio of D2 divided by D1, which is in this case 3.882, and the angle of the cone, which is 30 degree in this case, you just need to get the cross section between the x-axis and the line of the angle here, and finally you get the K value. Okay, so in the previous step, okay, we already list down all the info and we already sketch the formula of length, okay. So now we just have to substitute the value, the info that we got uh, into the formula, okay, in order to get the answer. So basically this is the output, okay, and this is, I just show it again, the layout of the formula. So if you can see here, okay, so this one is the D1 value, which is you get it from a table, okay. D2 as well you get from a table together with A1 and A2. So all of this actually you get it from the table based on the DO1 and DO2 value given from the question, okay. Alright, so this one is actually flow rate. Flow rate is actually originally provided from the question, which is 100 liter per minute. So I need to convert it into SI unit, which is meter cube per second. So this is our flow rate. And then once you get the flow rate, you need to get the V1 here. So this is the formula for V1. Okay, you will get this answer. And the ratio D2 divided by D1, okay, this one is because we need this value to use it for figure 10.6, okay, this is for x-axis value, okay, and from figure 10.6, okay, here, okay, you will get the K value, which is at 0.48, okay, and lastly, you substitute the K value and the V and the 2G into this formula, and finally you will get your HL, which is at 0.47 meter. Okay. Okay, another part is which is can contribute the energy loss, which is called as a sudden contraction. Okay, so sudden contraction occur when the liquid flows from a bigger diameter, okay, which is at D1, into a smaller diameter of pipe, which is at D2. Okay, so the V2 here will reduce in velocity. Okay, so again, for sudden contraction occur when D1 is greater than D2. Okay, so therefore, the formula to calculate the HL, the energy loss, is actually relies on V2 in this formula, okay, which is the V at the smaller pipe, okay, and K here is actually depends on the ratio between D1 over D2, which is the ratio of a bigger diameter divided by smaller diameter, okay, and the velocity at V2. Okay, so this is actually another table that you can use to get the K value. Okay, same as before. First of all, you need to get the ratio of the bigger to a smaller size pipe, which is involved in the flow. So for example, in this case, D1 divided by D2, okay, and then you have to get what is the velocity. So let's try. So for example, if you have your D1 divided by D2, which is equals to 1.2, and your V2 is actually at 3 meter per second. So this is your D1 by D2. Okay, so the value should be any value along this line, and then V is 3, so just goes like this. So this is actually the answer for K value, which is equals to 0.08. And same again, if you don't want to use the table, you can also use the figure. Okay, the x-axis is still D1 divided by D2 ratio. Okay, and then you have to choose what is your V2. So just mesh it with a point. Okay, so let's try, for example, like your D1 over D2, which is equals to 3, and your V2, which is equals to 9 meter per second. So what is your K? So let's try. So this is your D1 divided by D2. So it should be along here. Okay, so 1 is touched with the line of velocity here, which is at 9 meter per second. So this is the point that we are looking for. The intersection, you just straight away goes to the y-axis here, which is 0.36. Okay, equals to 0.36. Okay, very easy. You can use either one. Okay, so let's try to do this example for sudden contraction. Okay, let's read the question together. Okay, so determine the energy loss in water which is flow at 100 liter per minute. So obviously this one is actually Q, flow rate, from a large copper hydraulic tube to a smaller one with a sudden contraction. Okay, so it flows from a large part to a smaller part. Okay, so the larger tube has a diameter of, okay, so this one is actually DO1, which is actually 18 millimeter with this T1. Okay, the thickness of the pipe, which is 2.8 millimeter. And then the smaller tube dimension is actually DO2 at 25 millimeter. Okay, with the thickness equals to 1.5 millimeter. Okay, so you need to get what is your HL. So obviously it's clearly said that it involves in sudden contraction. Okay, so for sudden contraction, we know that in order to calculate the HL, okay, so we have to know what is the K, and then we substitute into the equation, and then we can get what is our HL. Okay, So let's see how can we determine the K value and the V2 value before we can substitute into this formula to determine the HL value. Okay, so as usual, to solve the problem, we have to list down first all the info given in the equation, and you need to plan your formula. Okay, so the equation wants you to determine the energy loss, which is the HL that occur in a sudden contraction, which is it flows through a sudden contraction. Okay, so the equation do provide us diameter of the pipe. Okay, so remember that this is the sudden contraction. That's mean this is the shape of sudden contraction. Okay, so this one we have the D1 and the D2 and V2. This is the three information which is important to get the K value. Okay, so from the equation we know that the smaller tube, which is D2, is given. Okay, so this is the smaller tube diameter, the outside diameter, and we also have the parameter of the thickness. But the one that we need for the calculation is D inside, the diameter inside. So from the outside, we can use table G2, okay, to get what is our D2. Okay, this one, I repeat, this one is actually DO2. So we need to get D2 from table G2. Okay, same again for D1, which is for a for a bigger part. Okay, so this one we already have the DO1. So we have to refer to table or appendix G2 to get the D1 value. Okay, same as the area as well. We have to get it from the table. Okay, and gravity acceleration, we know that. Okay, velocity is not given, but we can get it. We know that V equals to Q divided by A. Okay, and flow rate is given, okay, which is 100 liter per minute, and we have to convert it into SI unit, which is in the unit of meter cube per second. Okay, and this is the journey to calculate or to determine the HL value. Okay, so obviously we need to get what is the K value first. Okay, and in order to get the K value, we should know what is our V2 and then what is the ratio between D1 divided by D2. Then we will be able to calculate to determine the K value from this figure, from the Moody chart. Okay. Then after we have the K value, we have to get the V2 value. Okay, so V2 we just substitute into this formula. We need to get this V2 from this formula, which is Q divided by A2. Okay, and G we do have it and we knew the value already. Then we will be able to solve this equation and get the HL. Alright, so this is the Moody's chart that we're going to use for the sudden contraction. Okay, so first thing first that we should know what is the ratio between D1 divided by D2. So in this case, our D1 divided by D2 is 3.882, which is located here. Okay, and our V2, which is 4.385. So it is somewhere around between the line of 3, this is line for 3 and this is line for 3 and 6. Okay, so it lies between the 3 and 6. So you have to get what is the point, which is for 4.385. Okay, so as you can see here, I estimate it somewhere around there. So the K value is 0.42. Okay, so next thing is we have to substitute all the value. Okay, so if you can see there, we already have our K value that we get from this Moody's chart. Okay, so just substitute into the formula. Okay, so here we are. We have the answer. Okay, so this is actually the value that I got from the appendix for D1 and D2, A1 and N2. So once I know D1 and D2, I can calculate my velocity by using the flow rate. So the flow rate I have to convert first before I substitute to calculate the velocity here. Okay, so this is the formula to calculate the velocity. And D1 divided by D2. So using this ratio, D1 divided by D2. So I get the ratio is 3.882. Okay, so I have to use this Moody's chart. Okay, using the X and the V line to get what is the K. So here is our K. So lastly, you have to just substitute all the info here, which is K, V2 and 2G into this equation, and you will finally calculate your HL. So in this case, HL is 0.412 meter. Okay. All right. The next part is gradual contraction. Okay. So the shape is quite similar, or it's just opposite of the gradual enlargement. Okay. In which that for gradual contraction, okay, the liquid flows from bigger size into a smaller size of tube. Okay, so in this case, the D1 is greater than D2. Okay, so what happened is V will be depends on the V2 for the calculation of HLs in gradual contraction. Okay, so the energy will be lost substantially, and then again we consider the V2. Okay, and this is the equation to calculate the HL. Okay, in order to determine the K value, I will show you later how can we use the diagram. Okay, okay, so this is the diagram that we're gonna use to determine the K value for gradual contraction. Okay, so remember that the gradual contraction is like this, the shape is like this, in which that it will move from the bigger to a smaller, where it has kind of cone shape here, and this cone shape, it has an angle. So this angle is actually will contributes the value of K. So the K value is actually depending on what is the angle value and the ratio between D1 divided by D2. So D1 is actually diameter inside the bigger pipe, and D2 is actually diameter inside a smaller pipe. Okay, so if you look at here, it's still the same concept. You just need to know what is your D1 divided by 2. So for example, let's say D1 divided by 2 here, which is 2.8. Okay, so this is our D1 divided by D2, 2.8. And then let's say that the theta is actually 15 degrees C as 15 degree. So it touched this line. Okay, so you can just get the interception, and this is your K value, somewhere around 0.048 or something like that. Okay, okay, so if you look at here, it has two diagram. Okay, because this one, the one here is from the theta at 3 degree until 40 degree, and this one here, the theta is much bigger, which is from 150 degree until 15 to 40 degree. Basically, it's just an extent of this chart. Okay. Okay, so the next part that we gonna discuss is about the entrance loss. Okay, so entrance loss is usually when the fluid flow from a larger tank or reservoir into a pipe like this. Okay, so if you can see here, there are four categories. Okay, like this one is considered as inward projecting pipe. Okay, so if it's inward projecting pipe, so we just can use the K is equals to 0.78. Okay, so if you look at all this thing, you can notice that the difference is at this point, the entrance point here. Okay, so when does it call it as an inward projecting pipe? Okay, so if you look at here, it kind having like some like extra pipe, okay, which is goes inside the pipe, the tank area. Okay, so if it's that like this, okay, so we consider that K equals to 0.78. Okay, we're using the same normal equation to calculate the HL, which is K equals times with V to the power of 2. And in this case, we are using V2, V at 0.2 divided by 2G. Okay, so the second one is square edges inlet. So the square edges inlet, okay, if you look at here, so it is in a shape of square. Okay, so that's why we're using name as square edge inlet, and the K in this case is 0.5. Okay, and this one is another category which is called as a chamfered inlet. Okay, so it has kind of slanting surface like this. Okay, and it goes like that. Same goes to the other side, slanting a bit before it goes into the inlet pipe. Okay, so if it's referred as chamfered inlet, so we use the K equals to 0.25. Okay, and last one, which is called as a rounded inlet. So the rounded inlet is has kind of shape like this. Okay, so here it's actually in a rounded shape. So usually it will provide the R value. Okay, so it has many categories or many K value. Okay, but you can get the K value by knowing what is the ratio between this R over with the D2 here. Okay, so if it's bigger than 0.15, or we consider is as a well-rounded, so the K is 0.04. Okay, if it's 0, then we consider as 0.5. Okay, so imagine that if it's 0, that means it didn't have any radius, so it's actually similar to this one. Okay, which is 0.5. All right. Okay, so as I said before, okay, for the case of entrance loss is actually a special case of a contraction which is occur when a fluid flows from relatively large reservoir or tank into a pipe. Okay, so the fluid must accelerate from a negligible velocity to the flow velocity in the pipe, and the ease of which the acceleration is accomplished determine the amount of energy loss. Okay, and the value of resistance coefficient for entrance loss is actually depends on the geometry of the entrance. Okay, so if you still remember that there are four categories of the entrance loss. Okay, and the HL actually contributes to the effect of the energy loss in entrance loss. Okay, so let's try the example which is involve entrance loss. Okay, so from this question stated that we have to determine the energy loss which is involved water that flows at Q equals to 100 liter per minute from a reservoir into a copper hydraulic tube with the dimension given. So if you notice again, all the example, I keep using the same specification, okay, depending on the case. So in this case, it flows from a reservoir, okay, where this is the DO2, diameter outside of the tube, for this pipe here, okay. So you need to get the energy loss in two different cases, okay. So the first one is if it's flow through an inward projecting tube, okay. So this is the inward projecting tube, okay. And the second one is if it's flow through a well-rounded inlet, so like this, okay. So if it's well-rounded, so it is considered as well-rounded, we can just use the K here as 0.04. And if it's inward projecting, we can use the K equals to 0.78. Okay, so let's take a look. How can we solve the equation? Okay, so the solution is very straightforward. Okay, so as usual, you just need to list down all the info given in the equation, and we need to sketch what is the formula that we're gonna use. Okay, so for example here, okay, so the diameter of the pipe, okay, which is the smaller diameter here, okay, so it's given here, the diameter DO2, okay, and this one is the thickness. Again, the same thing, you have to get the D2 from table G2, okay, and A2 is not given, okay, so this one you can get it together with the D2, okay, by using table G2, okay, appendix G2. And acceleration, of course, we know the value 9.81. Okay, the velocity is not given, okay, but you can get it by using this formula. Okay, and the flow rate is given, but this one is in unit liter per minute, so you have to convert it first into meter cube per second. Okay, so then after that we can substitute into the formula, or we can find any necessary value that we need. For example, like D1 and A1 from the appendix. Sorry, this one is actually I refer as D2 and A2 because the flow is actually moved, okay, from a reservoir into a pipe. So this one is actually labeled as D2, okay. Okay, so the flow rate, we convert it into SI unit, and then we can get the velocity. And this is the formula to get the velocity, okay, because we have the flow rate value already, which is we convert it into SI unit. And A also we have the value already, okay, so then we will be able to get the V2. Okay, then after that we want to calculate the HL. Remember, we have two cases for A and for B. Okay, so for A, which is the category of inward projecting, okay, so for inward projecting, we know that K is equals to 0.78, okay, and then for well-rounded category, okay, well-rounded category, we know that the K is actually 0.04. So we have the K already. Then we substitute both of the K value into this equation to calculate the HL. And lastly, we will be able to get the HL for A, which is 0.764 meter, okay, for A in the category of inward projecting. And for B, which is in the category of rounded inlet, which is at 0.039 meter. Okay, very straightforward calculation. Okay, so we come to the end of part 2 video for chapter 6. Okay, so don't forget to watch part 1 and part 3 as well. So that's it. Thank you very much. Bye.